to 0. Here I have something similar. Let me show you exactly why it is similar. Alpha is an angular acceleration. By definition, alpha is the change in omega, the angular velocity over time. That is the change in time of omega, which was the change in angular displacement theta divided by time. That's how we learned it algebraically. If we did it in terms of differential equations, then we would say that alpha is going to be the second time derivative of the angular displacement theta. And this once again can be related as theta double dot, the second time derivative of the angle theta. So this equation can also be written as d squared theta over dt squared plus g over L sine theta is equal to 0. But this is not in the exact form as it is over here. Notice, for at least the second equation, I have the second time derivative of the angle theta plus something, k over m over here. Here it's g over L. Here I have x. There I have the sine theta. So now I'm going to invoke something. I'm going to invoke something. I'm going to invoke something which is known as the small angle approximation. Now, how many of you remember or know what a Taylor series is? Some simple series. Now, many of you more have taken calculus, so you must have learned series. But basically, a Taylor series is a way of representing any function as some type of series representation. Some of them are finite, some of them are infinite. In particular, the sine of an angle theta is approximately equal, if we go term by term, to be theta. Then it's going to be minus theta cubed over 3 factorial, plus theta fifth to the 5th power over 5 factorial, minus theta to the 7th over 7 factorial, plus theta to the 9th over 9 factorial, plus continuing forever. So it basically is taking factors of theta. So it's basically being all of the odd factors of theta, starting from n equals 1 to infinity, where this just represents sum. Remember the total sum. So we're just taking the odd values, so 1, 3, 5, 7, 9, etc. And it's going to be theta to that value n divided by n factorial. But remember, a factorial is that number times a number minus it. So this is 3 times 2 times 1, or 6. This is going to be 5 times 4 times 3 times 2 times 1, so it's going to be 120, and so on. And of course, this is going to be multiplied by -1 to the n plus 1. So that gives us our oscillating positive and negative. But in this, we invoke the small angle approximation, which says, let's imagine theta is very tiny. And remember, we're using radians now. Pi radians is 180 degrees. Pi is 3.14, which means 90 degrees. And since we're dealing with sine here, that's going to be the maximum, is going to be 1.57. So if we deal with something that's, say, going to be on the order of 10 degrees, that's going to be 1/9 of 1.57. So that's a number that's less than 0.2. So if we do that, this term is very small. We have to count for it. This term is a very small term that we cube and divide by a number. So that will effectively make this 0. This one we're now putting into the 5th power, even smaller, and dividing by another number. So the small angle approximation says that when theta is small, the sine of the angle theta can just be represented as theta. And this is specifically for radians. And in terms of degrees, this is valid for theta being about less than or equal to 15 degrees. So let's use this now. If we use it, let me take those two equations now and replace the sine of the angle theta with theta. The one that we learned algebraically. Alpha plus g over L theta is equal to 0. Where theta is that angular displacement that it's making. Or, in terms of its actual notation, d squared theta over dt squared, so the second time derivative of the angle theta, plus g over L times theta is equal to 0. These are our two equations of motion. We now add to this in particular that let us define omega squared is g over L, so that omega is the square root of g over L. So if I put omega squared in both of these, let's look at the second one. The second time derivative of the angle theta plus omega squared theta is equal to 0. That is in the exact same mathematical form as this one, in which this case was the second time derivative of the position plus omega squared x is equal to 0. Which tells me I'm going to get the same equation. And this equation tells me that theta at any time t is going to be a cosine omega t. So let me write that specifically as g divided by L multiplied by time plus b sine the square root of omega g divided by L, the square root, times time. And this is how you find why a pendulum also exhibits simple harmonic motion, similar to the simple harmonic motion that you saw for a spring. The same identical equation. And they have to be because they're both exhibiting this oscillation back and forth. For the spring, it's back and forth in a one-dimensional space. For a pendulum, it's back and forth in terms of the angle theta. Not in terms of x, not in terms of y, because both x and y are changing for the pendulum. X is moving left to right, y is moving up and down, but the angle theta is going from some maximum value to 0, to some maximum value to 0, to some maximum value. So it's oscillating about this point. Just like here, the spring is oscillating about the equilibrium length, the rest length of the spring. And once again, just with the appropriate initial conditions, we could just then say theta at a specific time is equal to a specific value. That will, if we chose it correctly, kill off A or B, and then our equation will just become theta at that specific time is equal to some specific value, say theta naught is equal to A or B, and then you just have theta is equal to that constant times either the cosine or the sine, omega t, where in this case omega is g over L. Now for both of these, the units of omega are going to be in terms of specifically SI units, 1 divided by seconds. The square root, or rather, if we just look at the square root of g over L, will give that. G is, as we remember, meters per second squared. L is meters. That gives us 1 over meters squared. The square root of that, 1 over seconds squared. The square root of that is 1 over seconds. Same with K over M. That'll give you 1 over seconds. However, we define it to be an angular frequency. An angular frequency means that we're actually dealing with rotation. Where if we look at a unit circle, meaning it has radius 1, at any position x, or any position here, instead of calling it xy, say such as this is x and this is y, it can be represented as cosine theta and sine theta, where this would be the angle theta. So cosine and sine represent a complete revolution around a circle. Here at this position, this would be theta equals 0, and notice cosine of 0 is 1, that's x. Sine of 0 is 0, that's why it's here. Over here, this is 90 degrees. The cosine of 90 is 0, that's why x is equal to 0. Sine of 90 equals 1, and that's why it's equal to that. And then they start becoming negative, to give you the negative values. But because of that, what we're going to say is because it's an angular frequency, we define it by radians per second. Because it's making an angular oscillation. So because we're representing it by radians per second, I just want to give you a definition. And that is, how do you relate the period? Now for a circle, the period would just be, this is start, it goes around 360 degrees, and this is end, where the start and end are the same. So the total angular displacement here is 360 degrees, or what we use, 2 pi radians. For the spring, what's a complete oscillation? Let's say I started off here. A complete oscillation is it starts here, it reaches the equilibrium point, compresses x, goes back to the equilibrium point, and gets to this extension point. So it's one complete cycle, where it started to where it ended. For the pendulum, same thing. If it started here, one complete period is it swings all the way to the other side, and then swings back. So start and end have to be the same. In that, what we're going to define is that omega is going to be 2 pi, the total angular distance. Because remember, what we originally had was, this was our definition of omega from rotational kinematics. It's the total angular displacement divided by time. And thus, if we did not know what it was based upon k over m, square root of k over m for a spring, or here the square root of g over L, we could always say that the angular frequency omega is going to be 2 pi, that's the total angular distance, c is a unit circle, divided by the period, which I give as a sort of t. And thus, if you knew what omega was, the period is just 2 pi omega. And both of these are related to each other. Basically, the 2 pi gives us the idea of an angular revolution, where any simple harmonic motion can mathematically or geometrically be related back to a circle undergoing perfect circular motion, where each point on the circle x is represented by cosine of the angle theta, sine of the angle theta is y. I remember what theta is. Theta is just omega t. And that's what we see in each of these final equations. Omega t, omega t over here. They just happen to have, for each physical system, a specific value associated to it. Square root of the spring constant k divided by m, pendulum square root of g, the gravitational acceleration, divided by the length L. And I should also note for this pendulum, I have made 2 approximations. I actually made 3 approximations for this. One, that the string is massless. If it had mass, that means there would be an added force, and the moment of inertia would not be exactly ml squared. So that would change the equation slightly. So I believe when you had it on your lab, they gave it to you in a different form instead of ml squared. And that's because the moment of inertia was slightly different from this very ideal case. The second is that I'm ignoring friction, which of course if there's friction in either of these cases, that will eventually slow down the system. For a spring, say on a one-dimensional plane, friction opposes motion, is a decelerating agent, and that's why instead of oscillating forever, each oscillation is going to get less and less and less until it stops. For the pendulum, there's 2 types of friction. One is air resistance, which is negligible, but also at the pivot point. Is this thing wobbling around any bit? Is it constrained? That could change its motion from just being strictly, say, 2-dimensional. It could make it 3-dimensional. Or it could give it extra oscillations beyond this. And the friction part could just slow it down. And the third is that the pendulum, this equation, the simple harmonic motion, is only valid for small angles. Meaning, let's say this angle theta, instead of being 10 degrees, if I made this, say, 89 degrees, and I let it go, it will not undergo simple harmonic motion. And mostly that's because the string itself is going to bend at different locations. So this string will not be a contiguous source. So this is only valid for small angles. So if you take a pendulum and go really high, you will not map out this entire equation. So only small oscillations does it work for.
Are those two equations different?
Which one?
The one with the kinetic equals pi and then the...
No, they're the same. I just solved them for each one. Because clearly if you... Oops. Thank you. That's a big oops right there. So the period clearly is going to be 2 pi divided by omega. Thank you. So change that in your notes. And of course that makes sense. Omega is radians per second, so it has to be in the denominator. So thank you for that. Yes?
Small angles mean under 15 degrees?
Yeah.
You say that the tension of the string is equal to the centrifugal force?
Yeah. But that wouldn't help you in this way to get this equation of motion.
No, but you can get the force of gravity from that.
Yeah. You could do that. Other questions about this? No. So let me remind you. Simple harmonic motion. The general equation for any simple harmonic system that obeys its oscillatory nature, where starting point and ending point are the same, and each time it has the same period t from start to end. And once again, we're ignoring friction in a realistic laboratory situation. We're talking ideal. They will always have this equation. Whether you're talking about the position that you're worried about or the angular distance theta, they all have the equation a cosine omega t plus b sine omega t, where omega is 2 pi divided by the period, or in each of these cases has a unique physical reference to them. And the way to simplify the equation is to use some initial conditions. To say if time equals whatever, it's given this value, plug it into the equations, and basically A or B should die off, and the other value should be equal to that value. So that's a general way that we would deal with these situations. Okay, so simple harmonic motion. Okay, so since we only have about 20 plus minutes left, I don't want to go into a huge idea of fluids and pressure, so I'm going to save that for next week. So let me just tell you what we're going to deal with. We have 4 lectures left. And with that, I'm going to deal with the idea of pressure first for liquids and gases. In this, we're going to understand the basic idea of pressure, and we're going to understand, for example, the idea of hydraulics. So it's really by our understanding, by a person known as Pascal, who, if you've ever learned very old computer systems, operating systems, Pascal, or Turbo Pascal, that was named after, also a mathematician, but he was the first person to understand that pressure in an incompressible fluid, such as water, is almost instantaneously exerted everywhere. So if you exert pressure on one point, you're exerting pressure on the entire system. That's how our entire engineering base, our entire infrastructure is built. How, for example, hydraulics are used. So what brakes a truck, the brakes in a truck, or even what we use for a crane or a forklift. All of that is using water, basically exerting pressure on water in one area, it exerts in all other areas, and then using other principles to see that the forces become magnified if you create the situation correctly. So really what we're learning is how everything got built beyond a few stories. Now remember, one of the great wonders of the world, 7 wonders of the world from antiquity, one of them was the lighthouse of Alexandria, port city in Egypt. And that lighthouse is what we would consider today maybe at most 30 stories. And that was the largest by far that anyone built. Basically, up until modern history, right before the turn of the last century. So until the late 1800s, that was as big as things got. And that's just because people couldn't lift things much higher. And they ended up having to use lots of animal power to build the Gothic cathedrals and other things just to lift everything. But of course, even animal power becomes limited at a certain point. So how is it that the skyscrapers got built? It's through hydraulics and through what we're going to learn in our next lecture. After that, we're going to learn other ideas of thermodynamics. Thermodynamics is the study of heat, where for gases, when you exert pressure on a gas, you also are going to change its volume and temperature. So we're going to have relationships between volume, temperature, and pressure for a gas. That is a compressible fluid. So the idea of incompressible versus compressible is, say, water is incompressible. If I had a cube of water, say just a cube of water, and it was completely filled, I could not compress that without having it spill out. It would not allow it. But a gas, if I had a cube of gas, if I just took a cube of gas, I could, of course, constrain that, and the gas could get smaller and smaller and smaller in volume, or bigger. And in that, we're going to learn about things such as, the main thing is the kinetic theory of gases. So how we can represent specifically temperature to kinetic energy. And thus, the temperature of this room, the average temperature of this room, is derived from the average kinetic energy of all of the gas particles in their random motions. Then I want to go to the thermodynamic equation, which basically says PV, pressure times volume, is related to, you might have seen in other ways depending upon what system you've taken it, nRT or NT or NKT. It's basically just molar numbers or actual number of particles times whatever constant you want, which relates it multiplied by temperature. So it's basically saying pressure times volume is directly related to the number of particles times temperature. That's the thermodynamic equation. And if we have time, I like to talk about the general ideas of a heat engine, which a heat engine is basically every engine that we see in existence. And in that, we would learn the idea of entropy, which people sometimes mischaracterize as disorder. But that's basically what we're going to do for the last 2 weeks. We're going to be talking about these ideas for it. Now, before I hand out the test, let me just remind you of a couple of things. One, I've put on Blackboard homework number 5.